My name is Janma Pati, and my project mate name is Uday Kumar Goel. We are presenting this project presentation, and the project title is Enhancing Grid Performance through Integration of Energy Storage System in Renewable Energy Systems. So here is our table of contents. So first is introduction, second one is project problem statement, third one is methodology, and fourth is review of energy storage system. Fifth is renewable energy integration. Uh, which energy storage system, ESS service for renewable energy integration, selection of appropriate ESS based on practical application and environmental impact. Last one is our conclusion. Surging demand for electricity and the pressuring air to the reduce greenhouse gas emission have led to a successful global expansion of variable renewable energy sources in recent years. Projections indicate that this trend will persist in the coming decades. In 2021, there was a notably 6% increase in a renewable energy capacity additions, reaching a historical high of 295 gigawatts in total installation capacity. This growth is primarily attributed to a significant rise in a solar in solar photovoltaic capacity, which increased from 134 gigawatt in 2008 to 151 gigawatt in 2021. The expanding power is poised to impact the existing electrical system and its operations. Dealing with the challenges posed by integrating fluctuating energy sources into the electrical grid offers various possibilities. One effective solution is energy storage, which addresses intermittent production by decoupling supply and demand and accompanies brief fluctuation. Energy storage has the potential to mitigate voltage variation, enhance system flexibility, and facilitate the storage and distribution of renewable energy. So this is our problem statement. There are basically three types of problem happens in grid level. One is transmission level, one is distribution level, and one is transmission and distribution level both. So at transmission level, there is a rotor angle instability, sub interactions, interior reduction, frequency instability, and increased flexibility requirement. And in distribution level, there are four problems: voltage regulation, reverse power flow, under over voltage, and protection issues. And in both transmission and distribution level, there are two problems: harmonic disorders and voltage instability. It is our methodology. So first one is we review all energy storage technology, and after that we make a renewable energy integration with energy storage system, and then after selection of appropriate energy storage system based on practical application, and the last one is environmental impact of energy storage system on the grid level. Start with review of energy storage system. So energy storage system offer an intelligent approach to address issues such as managing variation in power output, ensuring consistent frequency, stabilizing voltage levels, and enhancing the overall reliability of power supply. Energy storage system can be categorized according to the medium used for energy storage, which can take the form of mechanical, electrochemical, chemical, thermal, and more depending on the specific method of energy retention. As I mentioned above, there are many types of energy storage system. In this slide, we describe all types of energy storage system. The first one is thermal, the second one is electrochemical, and the third one is chemical, fourth one is mechanical, and last one is electrical. So there are four types of energy storage system in thermal as well. So packed uh, bed heat storage, latent heat storage, sensible heat storage, and HTTS. And there are six type of energy storage in electrochemical. First one is lithium ion, second one is vanadium redox, third one is lead polymer, fourth one is lead acid, fifth one is nickel, fifth one is zinc and barium NaS, and nickel chloride. So there are three types of energy storage system in chemical. The first one is fuel cell, second one is synthetic natural gas, third one is hydrogen. Let's go to mechanical. There are three types of energy storage system. The first one is flywheel, second one is pumped, hydro storage, third one is compressed hydro storage, and the last one is electrical. There are two types of electrical storage system. The first one is supercapacitor and the second one is capacitors. With renewable energy integration with energy storage system. Energy storage systems are becoming increasingly probable due to the capacity to assist the power grid by producing various services, including energy trading, reducing peak power demands, acting as a backup power sources, matching energy supply with the demand, maintaining voltage levels, ensuring frequency stability, and initiating grid restoration in the case of a blackout. Uh, So as I mentioned, there are seven types of power operation which is used to support power grid operation to maintain the grid stability and reliability. So first one is energy attributes, the second one is peak saving, third one is spinning reverse, fourth one is load following, fifth one is voltage regulation, sixth one is frequency regulation, and seventh one is black star. Describe this power operation in a brief. So first we start with energy attributes. So energy attributes significantly influence the economic aspect of the grid management as it involves utilizing energy storage system to generate financial gains by strategically purchasing and selling energy at optimal moments. The primary aim is to market power when prices are high and stop by during of low pricing. So it mainly helps to maintain the price of power. The second one is peak saving. Unlike energy attribute, peak saving has no economical focus. Its sole purpose is to manage and reduce peak loads. Peak saving utilize energy storage system to meet peak electricity demand. Additionally, it's worth noting that while peak saving systems are typically installed on the customer side, energy attribute applications are common set up on supplier side of the energy grid because peak power instants are brief and they strain and the grid and diminish efficiency. So basically the peak saving is used to merge the demand and supply whenever the demand is high. We pass the energy from energy storage system. Whenever the demand is low, we store the excessive energy in energy storage system. The third one is spinning reverse. A spinning reverse refers to a portion of an electrical system that remains idle during regular operating conditions. However, it is excessively employed address temporary power shortage. The primary function of the spinning reverse is to assist meeting electricity demand in event of a power outage. Fourth one is load following. The electrical power system frequently experiences fluctuation in a load, resulting in a server challenges in a grid management. Energy storage systems exhibit more excellent responsive than other forms of power generation as they can swiftly adapt to sudden changes. In this content, ES is primarily balanced power generation and demand. It is also well suited for tracking load variation, whether they increase or decrease. So load following is basically the function which is used to whenever there is a like immediately uh, increase in a load at the time we supply the power from energy storage system. So there is no grid tension in the grid just because of energy storage system. Let's start with the voltage fluctuation. Fluctuation of voltage significantly influence grid stability. Ensuring voltage remains within its allowable limits is crucial to uphold system stability. Voltage support is essential to transmit the reactive power over extended distance, and energy storage system can play a supportive role in this application. So what this means? Uh, we can transfer the power to long system by using energy storage system, and we also maintain the voltage level so we can so there is a minimum loss of energy during the long transfer of power. The sixth one is frequency regulation. Frequency is crucial in preserving the balance between power generation and demand. Effective frequency control is necessary to ensure the frequency remains within the desirable range, typically around 15 Hz. Energy storage systems are frequently employed alongside frequency regulator to help maintain the desired frequency levels. The last one is black start. Breakout in the power system result from unexpected disruption in individual components or the same entire system, posing a risk to system stability and leading to a power outage. Energy storage systems have various applications, including aiding in the black star scenario. In such a situation, ESS assist in a voltage support, balancing the relationship between the grid and consumer, and serving as an initial power source for the traditional generator. So, after this slide, my colleague starts the presentation.
Energy storage system service for the renewable energy integration. The benefit of using energy storage system to integrate renewable energy into power grid are mentioned below. The first operation is solving intermittent generation of renewable energy. The second one is the frequency stabilization. Third one is the voltage compensation. The last one is to prevent backfeeding. The first operation is solving intermittent generation of renewable energy. The renewable energy generation depends on environmental factors like wind speed, solar radiation, and temperature, making it unpredictable and subject to intermittent fluctuation. So this variability complicates its use into meeting electrical demand within the power grid. So consequently, energy storage systems play a valuable role in mitigating this challenge by stabilizing and regulating power output from the renewable source. And the second one is to maintain the frequency. So to do that, it is necessary to introduce excess energy quick, uh, quick way to adjust the system frequency. Typically, I demand a rapid response within the second and a few minutes. Achieving this necessity, energy storage system with a swift response time, excellent performance capability, and high power output capacity. Whenever there is disparity between the power generation and system demand, energy storage systems are required to oversee and stabilize system frequency. Third operation is voltage compensation. A coordinated voltage compensation approach was introduced to control the voltage in the distribution network. This method involves using multiple distributed energy storage systems and theoretically divide the grid into various regions, and each of which has its voltage regulation handled by a distributed energy storage system. Distributed energy storage systems were employed to attain voltage compensation in grid with significant concentration of renewable energy source. The last operation is prevent feedback feeding. The feedback feeding within the power network is characterized by electricity flowing in the opposite direction to its usual path. The accidental backfeeding occurring for corresponding risk to system equipment and safety of ser- service personnel. Integrating renewable energy source into distribution power grid has increased the potential for the backfeeding risk. Energy storage systems are employed to achieve greater self-utilization of renewable energy power and reduce excess RE production. Framework of energy storage system for renewable energy integration. In this figure, we can see that we have wind turbine and solar PV panel. So power from wind turbine uh, can be stored into supercapacitor and battery through voltage AC bus, and power from the solar panel can be stored into battery again through the voltage DC bus. Then this power can be stepped up by using the step up transformer, and then we connect this two line to the medium AC bus, and from medium AC bus we can use step down transformer, and we from step up transformer we can distribute power to the housing load. And we can see from the figure that we have circuit breaker. So if sometime if there any circuit, if there any if there any force occur, then it will cut off this system from the grid. Second framework is related to the DC microgrid. So here we have DC bus bar, medium DC, low DC bus bar, and a medium DC bus bar. Here, this is a framework of hybrid power system. Selection of the appropriate energy storage system based on practical application. For example, if we want more power capacity, storage capacity, we can use a pump hydro storage, compressed air storage, thermal energy storage. If we want more thermal power efficiency, cycle efficiency, we can use pump hydro storage, flywheel storage, battery energy storage system, supermagnetic energy storage system, and supercapacitor. And for if you want environment friendliness, then we can use thermal energy storage, flywheel storage, supermagnetic energy storage. So based on the uh, uh, different recommendation, we can use different energy storage system. Environmental impact. Various energy storage technology exhibit diverse environmental impact. Solar fuel stands out as an environment-friendly option, utilizing renewable solar energy to generate and store it green fuel such as hydrogen. These approaches offer the potential to reduce reliance on fossil fuel. On the other hand, complex energy storage, battery, and superconducting magnetic storage and pump hydro storage pose environmental challenge. The construction of pump hydro storage involves deforestation for reservoir, negatively impacting the ecosystem. And compressed air energy relies on the fossil fuel combustion, raising concern about emission. Battery, particularly lithium-ion and lithium magnesium type, generate toxic waste, resulting in harmful environmental effect. SMES operation present a significant environment challenge due to magnetic field and its produce, which can potentially harm both human and animal. In addition to the environmental challenge, production of recycling battery involve metals and non-metals for sustainable health and environmental risks. Exposure to metals such as lead, cadmium, mercury, arsenic, and chromium through various pathways can have detrimental effect on the human health. Battery waste containing toxic components pose growing challenge due to its abundant durability and increasing demand for the battery. The production of lithium batteries involves advanced technology, making them challenging to compare with alkaline battery in the market. The high cost of associated with production process, material and auxiliary system, along with safety concerns, contribute to the complexity of this composition. Lithium battery in particular requires assembly in the environmental with low humidity level due to safety consideration. Corrosive battery electrolyte if leaked during storage, use or transportation can pose risks with dissolved metal like lead potentially contaminating water or soil mobile chemical form. Moreover, waste water generated during various battery processes, including manufacturing, treatment, and recycling, contain hazardous elements such as heavy metals and electrolytes. If not properly managed, contaminated water waste can lead to the ground and surface water pollution, posing serious risk to the human health. Therefore, capturing and treating water has become crucial for the mitigating this environment concern. This secondary product focus on integration energy storage system which enable energy for enhanced grid performance. To highlight the growing need for sustainable energy and the challenge for intermittent renewable, emphasizing the necessity for a stable grid solution. An actual review of various years technology underlines a crucial role in addressing transmission and distribution challenges. So, a practical application of ES in the diverse power grid scenario offering essential services such as energy attribute, peak shelving, and frequency regulation. Comprehensive comparative analysis aids in strategically selecting ES based on the specific attributes for the various power system applications. Emphasize the environmental impact of different storage technology, advocating sustainable practice and continued research. Recommending fresh advance into technology, considering environmental implications and fostering collaborative effect for the challenge sustainable energy future in changing energy language. In this way, we can integrate energy storage system in the grid to enhance the overall performance of the grid. So this is our final project and thank you for listening to the presentation.